Hello.
Slides.
Sure, thank you.
Yeah, so Shobana, I'll give you an indication after 6 minutes. You'll have a total of 8 minutes. So 6 plus 2 and then 2 minutes for questions. Yeah?
Thank you. Okay. So good afternoon everyone. I am Shampurna and I am going to present our recent work on fractional extrusion statistics driven quantum heat engine. So we ask a very simple question: can quantum statistics serve as a resource, serve as a thermodynamic resource? This is a brief outline. First, I will introduce the idea of fractional extrusion statistics and explain how it generates particular symmetry breaking and which leads to a thermoelectric effect. And this helps us to exceed the known limit of the maximum power output of a quantum heat engine. So the traditionally particles are defined in two types. So by the behavior under exchange. So if we exchange two bosons, it generates a phase of +1, and whereas for fermions it generates a phase of -1. And in two dimension there are particles called anions which continuously interpolates between these two limits. Now we want to ask, what if we interpolate between them through generalized extrusion statistics? So this brings us to the idea of Haldane extrusion statistics. So this is the statement for the statistics. So for a fixed system size, the change in the number of available states, that is delta D, is related to the change in the number of particles delta L delta N by this equation, where G is a statistical parameter which defines how much states we occupy by adding a single particle. So for bosons, G is equal to 0. That means bosons does not exclude each other, and for fermions, G is equal to 1, which recovers the Pauli exclusion statistics. So Wu gave the distribution function. This is the distribution function, and we calculate. If we calculate the entropy density, it happens that the entropy density has a maximum at around the chemical potential. But the maximum entropy density deviates from the value of Kb log 2 for G not equal to 1, which actually are direct consequence of particular symmetry breaking. This can also be seen from the distribution function plot. So for G equal to 1, that is for fermion, it has a value of 0.5 around the chemical potential. That means there is an equal probability of finding a particle on hole. But that is not the case for G not equal to 1, and this we call as a particular symmetry breaking. Now, since there is a particular symmetry breaking, the natural quantity is to see is the thermoelectric effect. So we do a transport measurement in this setup. So we have two reservoirs kept at different temperatures and voltages, and in between there is a scattering region defined by this transmission function T. And this is the equation for the charge current from the Landau-Boettger formalism, and we do a linear response calculation. So to start with, we take the ballistic limit and we see there is no thermoelectricity. So we need to go to the energy dependent transmission function. Now there could be two sources of a thermoelectric effect. One could be from the transmission function itself, and another one is from the distribution function. Since we want to probe the particular symmetry breaking from the distribution function, we take an particular symmetric transmission function. And this shows that for G not equal to 1, we can have a finite Seebeck coefficient, whereas the fermions shows a 0 Seebeck effect. So since now we have a thermoelectric effect for G not equal to 1, we want to apply it in the heat engine platform. So the maximum efficiency for a heat engine is bounded by the Carnot efficiency, but at that efficiency the net power output is 0. So real engines we want to have a finite power output. So Whitney showed us a limit that for a fixed temperature bias, if you optimize the transmission function and if you optimize the chemical potential bias, you can there is a universal bound on the maximum power output for a heat engine. But so this is the bound for the and that is for the fermionic carriers. But is this an universal bound? So the answer is no. It depends on the statistics of the carriers, and so if you And this can be seen from this curve. So if you go from the fermionic limits and continuously interpolate towards the bosonic limit, the maximum of the power output of the heat engine actually monotonically increases towards the bosonic limit and hits the maximum at the bosonic limit, which has a value of log 2 square kb square TL minus TR whole square. Now interestingly, the maximum, the chemical potential bias required to reach this maximum power output decreases when we go from the fermionic limit to the bosonic limit, and this is an advantage actually. Now if you see the maximum efficiency of the heat engine as a function of the power output, so here we have plotted for 3 different temperature ratios and for various G values. So for any temperature ratios, this curves actually meets at the, so this black line shows the Carnot efficiency for that temperature. So this all the curves meets the Carnot efficiency at 0 power limit, but if you see at a finite power limit, the bosons performs better in terms of the efficiency than fermions. Now we give you an experimentally realizable setup of this heat engine, and we want to implement the bosonic carriers. So for that we take a one-dimensional ferromagnetic spin chain. So this is a central region, and the two sides, these are the two semi-infinite leads of the ferromagnetic spin chain, and this is the Hamiltonian. Now if you perform a Hall05 transformation, this allows us to convert the spin excitations into bosonic excitations, and with that we calculate the transmission function following the Cayley formula for transport, and we take the magnetic field. So this is the relation of the magnetic field, which can be taken as the magnetochemical potential. So
you have 6 minutes.
Yeah. So this is the transmission function which we want to engineer from this spin chain, and this gives us a nice platform to have the required transmission function we need to maximize the power output of the heat engine. And we can also tune the magnetochemical bias by this magnetic field. So this gives us a platform for our experimental realization of our theoretical predictions. So now I will conclude. So what we have done, so we have first seen the Haldane exclusion statistics can give rise to a thermoelectric effect. Next we incorporated this thermoelectric effect as an resource for the quantum heat engine, and it actually shows that once we go from the fermion to the bosonic limit, the maximum of the heat engine, maximum power output of the heat engine actually increases. So we found a new bound for that, and next we provided the experimental setup to realize the bosonic heat engine in one dimension. And so as a final note, so what we have established is that quantum statistics can actually serve as a resource for the thermodynamic setup, and this can enhance the maximum power bound of an heat engine. So if you are interested, you can see more details in these two manuscripts. Thank you for your attention.
Yeah, thanks, Shampuna. So, questions from the audience?
Yeah, Sampurna.
Yes.
So how to extend it from 1D to 3D? Then the comparison becomes very easy. Na?
Yeah. Mm-hmm.
You showed some experiments, but still if it is extended to...
Yeah, we need 3D. Yeah. We have to work on that, yes.
Yeah, maybe you have to modify the Hamiltonian accordingly.
Because this LA statistics is realizable in any dimension. It is not bound to 1D or 2D or 3D.
Yeah, maybe you can think about extending it for
Yes,
3D.
yes, sure.
Okay. Any other questions? Okay, so if not, thanks Shampuna for this talk.
So hi everyone, I am Jyoti and I'm a research scholar at in Department of Physics at IIT Kanpur, and I'm delighted to give a talk on strong acoustic phonon suppression leads to ultra low thermal conductivity and enhanced thermoelectric performance in barium, copper, gadolinium, tellurite. So thermoelectric materials are basically the ability of a material to convert the heat into electricity and vice versa, and these are Hello. Okay. So, so the performance of a thermoelectric material is characterized by this figure of Marrott, which is dependent on the Seebeck coefficient, electrical conductivity, and in the denominator we have the electronic thermal conductivity and lattice thermal conductivity. So in principle, on paper it seems very simple to tune the ZT factor. We can improve the conductivity and decrease the thermal conductivity, and we are good to have a good thermoelectric material, until the Weizmann-Frenz law came into picture, which tells us the electrical conductivity is directly proportional to the electrical thermal conductivity, which limit our capability to tune the ZT factor. So instead of focusing on the coupled parameters, we will focus on the lattice thermal conductivities, which is an independent quantity, and we will try to find a material which has intrinsically low lattice thermal conductivity, or we can tune the lattice thermal conductivity using nanocrystallization or defects introduction and all. So that was the reason for choosing this particular compound, which belongs to the quaternary chalcogenide semiconductor family. This has a layered structure, and the layer forms a strong covalent bonding, and these layers are separated by Ba atoms. And this family is known to have very low lattice thermal conductivities because of the structural distortion present within the layers, and also the presence of anti-bonding interactions. So that is evident from here. The lattice thermal conductivity of this compound is very low. It is of the order of 0.15 watt per meter per Kelvin at room temperature, which is considered very low for the thermoelectric applications. So also the electronic structure of this compound shows that it has a band gap of 0.54 electron volt, and this has strong covalent bonding within the layers, and due to that it is expected to have good electrical transport as well, and that is evident from the effective masses as also, which has a very small quantity, small in number. So now the question arises how we can calculate these transport properties like the Seebeck coefficient, electrical conductivity, or the thermal conductivities. So the formalism which we have used is by solving the Boltzmann transport equation, which basically tells us the change in the distribution function in influence of some external perturbations. The perturbations can be the temperature gradient or the electric field. So this is the Boltzmann transport equation, where the first term is the explicit dependence of the distribution function with upon time, and this is the diffusion term, force term, and the collision term. The electron are getting scattered from the lattice, and that quantity is quantified by this collision term. And in principle, it is very difficult to calculate the collision term, and we use different approximations to solve this, and one of the well-known approximation is the relaxation time approximations, basically in which we consider that it takes a constant time for the system to come back to its equilibrium after particular scattering happens. So if we want to calculate the electronic mobility, which will eventually connected to the conductivity of the material, we will apply an electric field across a material, and the mobility is dependent on the change in the distribution function with respect to the applied electric field. And by solving the Boltzmann transport equation under the relaxation time approximation, we will get the change in the distribution function with respect to electric field, which is dependent on the scattering rates, and the mobility is eventually we can get from by calculating the scattering rate and the group velocities. So in principle, to calculate the scattering rates, we use the Fermi-Golden rule, where electron can scatter. So either it can absorb a phonon or emit a phonon, and this is quantified by the Fermi-Golden rule. And this scattering rate is dependent on the electron-phonon coupling matrix, which is dependent on the initial state of the electron and the final state of the electron after the emission or absorption of the electron, and the change in the self-consistent potential of the electron when it interacts with the phonons. So in principle, it's very difficult to calculate the electron phonon, not difficult but computationally expensive, because we want to calculate the transport properties. So we have to sample the Brillouin zone with very dense grids. For the transport calculation, the grid requirement is of the order of 100 cross 100 cross 100, and also we need the information of the electrons as well as phonons, and DFT scales with the number of atoms in the system as n cubed, and DFPT calculations scales as of the order of n4, n raised to power 4. So electron phonon coupling matrix can be as large as this much, and this is some example, even the electron phonon coupling matrix calculation on a very coarse grid for such small systems takes that much time. So, and our system has 12 atoms. So in that case, it is not feasible to go with the DFT and DFPT directly. So instead of doing that, like now the question arises how we will calculate the electron phonon coupling matrix on finer grids. So instead of going for the fully first principle approach, we define phenomenological models, like there can be possible scattering can happen in a material. The electron can can scatter from the acoustic phonon modes, and it will create a deformation, it will feel a deformation potential. So, and it can, like if the material is piezoelectric, it can scatter from the electric field due to the piezoelectric nature, or it can scatter from the optical phonon mode, or if there are some ionized impurities are present in the system, so that can scatter, that can also scatter the electrons. So we define different models for these possible scatterings, and we define model in such a way that these electron phonon coupling matrix corresponding to these scatterings are dependent on the material properties, like the dielectric constant or the elastic constant, so and these are not computationally that expensive to calculate in DFT. So then from that electron phonon coupling matrix we will get the scattering rates, and using the Matheson's rules we can get the total scattering rates from all 4 possible scatterings, and correspondingly we can get the transport coefficient, which is dependent on the scattering rate and the velocities. And this is the result. Like this approach has shown very good correlation with the experimental values, and this is our result. Like from the generalized transport coefficient, the different moments will tell us the Seebeck coefficient or the electrical conductivity, and this is the result. Like the electrical conductivity and Seebeck coefficient we have shown for 4 different concentrations for the p-type doping, and it is shown that it is better than some of the well-known thermoelectric materials like the lead telluride and tin selenide. And this is the final result. This is the ZT factor, and these are the power factors different to as a function of temperature for 4 different concentrations, and we have considered both the concentrations n-type and p-type. So power factor is basically the square of the Seebeck and the conductivity, which is shown here, and correspondingly the ZT factor is shown here, and we have reached a ZT factor of 2.1 for the n-type doping and 2.3 for the p-type doping, which is considered very good, and it is almost equivalent to 20 to 30% efficiency of a Carnot engine. So this can be a potential candidate for the thermoelectric applications. And with that, I would like to thank the organizers for giving me the opportunity to for this presentation, and my supervisor for Professor Kaushik Pal for the constant support, and also my lab mates for their scientific discussions. And thank you.
Okay. Thanks, Jyoti, for the talk. Questions from the audience? Okay, if not, I have a very general question for you. I'm not from the field, so this question. Maybe you said it, but I missed it. What is the motivation for choosing this particular material? In the end, I understand that's a fantastic material, but right at the beginning, what was the motivation?
So this belongs to a quaternary chalcogenide family. So this family is known to have very low lattice thermal conductivities in general. So it has structural distortions as well. This structure was enharmonicity in this this structure has enharmonicities, so that all those factors lead to very low lattice thermal conductivities in this.
Okay. Okay. Super.
Nice talk. Actually, I missed a few initial slides of your talk, but I have one question. How do you do the E-type and N-type doping in your material? Actually, you do some elemental substitution or something else?
No, in principle, we define models, so there we can define the concentration, but in experiments, obviously, we have to dope it with some material like
some atom.
Yeah, some atomic doping we have to do in experiments, but in case we just define the concentrations.
Okay, so I think we'll stop there. So thanks, Jyoti, for this talk.
So, good morning everyone. I'll be presenting our work on tunnel rate controlled heat distribution within mesoscopic circuits. So, to give a brief introduction, so a two-dimensional electron gas is one of the prominent platforms for many quantum transport experiments. including realizing spin qubits. So these are basically quantum wells which are formed at specific interfaces within a heterostructure due to engineered band mismatches across the interface. And for the specific case of a gallium arsenide, aluminum gallium arsenide heterostructure, the interface forms here, and it gets populated by carriers from a modulation doping layer. And when the temperatures are low enough, only one level would be accessible within the well, and that gives a confinement along the epitaxial axis, defining a 2-deck. And then further confinements can be defined within the 2-deck by gate voltages. So a negative voltage would deplete the 2-deck, and hence a proper design, depending on the design of the gate structure, you can have the required like potential landscape of wells and barriers within the 2-deck. So observing any quantum transport phenomena within a 2-deck requires the electron temperature of the 2-deck to be lower than the respective energy scales. However, the multiple electrical lines which run through the cryostat, starting all the way from room temperature, bring in a lot of noise which heats the 2-deck. And further, since the electron phonon coupling between the 2-deck and the lattice weakens as the temperature is reduced, this cooling the lattice does not cool the 2-deck. So this keeps the 2-deck temperature much higher than the crystal temperature, even when the lattice is properly thermalized to the cryostat. So beyond improving the thermalization and filtering within the cryostat, other techniques for managing this heat is worth exploring. So one alternative would be to take advantage of this weak electron phonon coupling to redistribute heat within different parts of the 2-deck. So we use quantum dots for this purpose. So as discussed before, a quantum dot is confined in all 3 spatial directions, and hence giving it a discrete energy spectra. And then this quantum dot is coupled to the remaining parts of the 2-deck by tunnel barriers. And a net tunneling event can happen across the dot whenever there is an energy level available within the transport window. And this can be driven by either a voltage bias which offsets the Fermi levels, or by a thermal bias which causes different smearing. In either case, the energy spectrum being discrete gives energy filter for tunneling. And for the specific case where the transport is driven purely thermally at 0 source drain bias, the magnitude of this tunneling current would be decided by the tunnel rate, while the direction would be decided by the position of the dot energy level relative to source and drain Fermi levels. And all 3 of these are hence controllable by gate voltages. So this concept of energy selective tunneling to cool Fermi reservoirs have been demonstrated in other systems, like a metal insulator superconductor tunnel junction, where the superconductor's energy gap gives the energy selectivity here. But however, the prospect of using quantum dots for this purpose are not explored much, except for this one work where they use the relative detuning between 2 dots to cool a reservoir in between. In our work, we use the tunnel rate of a quantum dot, a gate-defined quantum dot, to control the heat flow between 2 points in a 2-deck. And we choose a quantum dot because for a tunnel barrier, you don't have energy filtering. And for a quantum point contact, there is no independent control over the tunnel rate and the level positioning. So the device is fabricated by, first of all, defining ohmic contacts to the 2-deck, then by etching out the 2-deck in the required geometry, and further by fabricating gate electrodes by a series of lithography and thermal evaporation steps. The device is then wire bonded and mounted at the mixing chamber, the 10 millikelvin flange of a dilution refrigerator. And so for this experiment, the gates colored in blue are powered to form a quantum dot at this particular position. And the gate pairs CBMB and CBRB form the 2 tunnel barriers between source and drain, while RP is the plunger gate which allows us to shift the energy levels of the dot relative to source and drain. So the device showed the characteristic Coulomb diamond signature, and for the experiment we controlled the tunnel rate by means of the gate voltages at the 3 barrier gates, and the electron temperatures at source and drain are estimated by fitting the quantum dot thermocurrent to a first order tunneling model. And the quantum dot thermocurrent is obtained by a line cut at the center of the Coulomb diamond. And the line shape of this thermocurrent is basically can be understood by the energy level diagram. So basically, since only a single level is involved, it traces the line shape of Fs minus Fd, which is the difference in Fermi distributions across source and drain, and that gives 0 current at the center and non-zero current of opposite polarities on either sides. So This is a plot of the temperature difference delta T across the quantum dot as a function of the quantum dot tunnel rate at 3 different heating powers at the source side. So we can see that delta T is indeed controllable by the QD tunnel rate, and that temperature differences as high as 650 millikelvin can be sustained across the quantum dot, whose diameter is around 370 nanometer. And we also find that the extent of this control, it comes down as the delta T value approaches the lattice temperature, which is closer to 0 heating power. And so these are the corresponding plots of source and drain temperatures for this data, and the sudden increase in the drain temperature between the in the regimes shaded in yellow suggests that at the tunnel rate, at the lowest tunnel rate of 575 megahertz, the heat flow to the drain side was restricted by tunnel rate, which is lost from 735, the next data point of 735 megahertz onwards. So additionally, we demonstrate a gate pulsing method to get an experimental estimate of Fs minus Fd. So this is done by giving a square pulse to the plunger gate Rp, and the pulse gate spectroscopy plots when the transport is driven by a voltage bias is well known. We study the thermally driven counterpart of this, and we observe this distinct branching pattern, and by analyzing the energy level diagrams at the different points within the plot, we interpret that this branching point, which is marked by the magenta solid line, happens when the gate pulse amplitude equals epsilon 0, which is the separation between the two extrema of Fs minus Fd, and these are further confirmed by simulations of first order thermocurrent. And also, so when we, as we increase the heating power at the source side from 0 to 40, we find that as expected, the branching point shifts to higher gate pulsing amplitudes, confirming the interpretation. And we additionally note that this branching point, since the gate pulse amplitude probes the energy axis of Fs minus Fd, instead of fitting to the line shape of the thermocurrent, line shape or amplitude of the thermocurrent, the only possible error in this branching point can come from the lever-arm conversion of the gate voltages to its energy. So to conclude, we have demonstrated a gate tunable control of heat flow between 2 points in a 2-deck, and we have also demonstrated a gate pulsing method to get an experimental estimate of Fs minus Fd, which probes the energy axis of the function. And regarding future possibilities, so using quantum dots itself for heat management is always an advantage, because we are trying to address quantum dot based circuits. And secondly, the operation of quantum dot based thermal machines can be switched between refrigeration and heat engine aspects by just the source drain and gate voltages. So it's convertible, it's flexible. So it's a promising aspect in that direction. Thank you.
Okay, so thanks Parvati, and it's tough luck to see so less audience. Does the audience have questions? If not, I'll ask you one or two questions. So number one is like, so you have your chip at 10 millikelvin.
Yes.
So what is the electron temperature at the gas?
Yes, that was what I was. So that can be tuned by our tunnel rate.
That I understand, but like
Lower limit was 320 millikelvin.
yeah. So if it was 320 millikelvin, like you have that large like 0.6, like how are you then achieving
Yeah.
that?
So we are also applying. Oh, yeah. So I think I forgot to explain this. So in the circuit at the source side, we are also applying white noise through a bias T to controllably heat the source side. So when that heat is 0, so these are at the these three curves are at different magnitudes of that heating power. So when that heat is 0, the TS and TD we have are around 310 millikelvin, and the difference becomes comparable to the lattice temperature. That is why we don't see much modulation here. But when we put an intentional heat, that difference is tunable with this.
Okay, and like when you do this procedure,
Yeah.
Does it affect the quality of your, like, because ultimately I guess you are trying to do some silicon quantum computing with this, right? Like,
Well, long-term goal, yes.
or not now?
I mean, my work is was mostly on gallium arsenide and doped silicon. I have not worked on undoped silicon.
Okay, so like when you do this procedure, like do you, like does the quality of your quantum dot get affected?
So quality as in,
It means, I mean, like the Yeah, I was more asking from the point of view of like qubits. So I guess that's not relevant in your case. You ultimately will try to like put in an electron in the quantum dot and try
Yes,
to
so
analyze one.
actually the motivation for this was that in our initial quantum dot experiments, the electron temperatures were high because of all the unintentional noise from the measurement setup, and we were looking at ways to control that.
Right.
Then, this was our second or third, trial. So in the initial trials, it was really high. So then, this method is actually, so one thing is, if the total noise reaching at one point of the 2-deck, which is mostly through the source side, if that can be isolated from the rest of the 2-deck, then that side is cooler. So that was the motivation.
Okay, good. So thanks a lot. So,
Okay, thank you.